Actually, this is a special session. It's not a junior academic session. It's the goal of this session is to give you an overview of the paper which has received the CNIL-Inria Privacy Award this year. Well, actually, I should say which will receive it on Friday, because officially the prize will be given. It will be on Friday at 11:45 in the Grand Hall. So it will be in presence of Isabelle Falque-Perrotin, the president of INRIA. So today, it's not the day for big speeches and formalities. The goal is to give to the winners the opportunity to share with us, I would say, the essence of their work. So it's a prize which is given by the CNIL and INRIA. So myself, I'm a representative of INRIA, and I'm here because I had the honor to chair the committee this year. And I just want to say that the committee was appreciated the paper a lot. We thought it was a perfect example of research effort with practical applications to improve privacy protection. And we think that it's a type of work which is especially necessary today with the advent of the GDPR. If we don't have more of this work, there is a risk that GDPR is not effective at all. So again, I would like to congratulate the winners. So Claudia Diaz, Carmela Troncoso, and Seda Gurs. And I just want to give the floor to Carmela for this short presentation.
Thank you, Daniel. Can you hear me well in the back? Should I use a mic? No? Fine? Cool.
Sorry, use a mic for the recording. There's no audio, if that's possible.
Okay. That's better? Is it working? Now? Yes. Well, thank you, Danielle, and I would like to thank the committee because we feel very honored of this award. This is a line of research that we have been working on for several years with here Claudia Diaz and Seda that sadly could not be here today. And all of it started because a bunch ago some people started saying like this privacy by design thing, like we want to have it. It started a little bit with the Information Commissioner from Ontario, pushing this forward, pushing the idea that privacy is something that has to be put up from the setup system. We have to think it from the beginning. Then came the GDPR that actually also is trying to push this concept forward. To be fair, in the latest draft, it moved from privacy design to data protection by design. This is another story. We can have another talk. Maybe another year they give us another award. But for today, I'm not going to talk about this one. But what we did here is that all of this was great. Privacy by design is great. We love it. But actually, we're engineers. So how do we do this? We work on a computer. We code on a computer. We design architectures. We decide to tell the computer what to do. And when we tell it, hey, do privacy from the beginning, it doesn't know what to do. So how do we let the engineers know how to implement this thing that is pushed from the top, from policymakers? And we started from the observation that in the academic world, like we have been for the last, I was working on privacy technologies for the last 10 years, and every year there are more and more systems proposed that have kick-ass privacy. Like we're great at this. But then when we're trying to get to the real world, none of this gets there. So the question is, why is it? It's not only a question of motivation, which there is, people like the data, but it's also a lot of question of not knowing what to do. And then we were wondering, like, is this privacy engineering a craft? It's something that you learn like painting or like a piano is something that you need to have this, or we can actually make an engineering discipline out of it. So we started to thinking, how do we articulate what the design process that we follow in papers to be able to transmit it to engineers so that this can actually get to the real world. And back in 2011, we wrote the first version of this paper. That's what the second one is reloaded. And we said, based on 2 case studies, one that was anonymous e-petitions. So this was a way of doing petitions to a city hall electronically in such a way that you don't need to provide your identity, but you can prove that you're part of that city hall, and if there were duplicate petitions, they are detected, but still my identity is not revealed. Or another system we designed for privacy-preserving road tolling, in which we could charge system depending on how much they drive, but without knowing where do they drive. And then coming up to these systems and thinking about, we were like, Claudia said and myself, thinking like, hey, what we did here, and we said, the key is data minimization. We're minimizing the data. We're minimizing the data like there is no data in the server about identity, there is no data in the server about location. Data minimization is the key. But then thinking more about it, like data is not really minimized. Data exists in the system. It's still in my car where I have my location, and my identity is still of my ID card or on my local computer where I use to actually transmit it to the city hall. So the data is there, or maybe the data is sent encrypted to a server, but the data is there. And maybe it's distributed among several servers to decentralize, but data is not minimized. So data minimization is a bad metaphor that we could not use to transmit again to engineers when we talked to them, what they were doing. So we started to think about, so what's that we do? And then we came up to this unpacking of data minimization, and we found that the ultimate goal that we find in all of these academic papers, and that you will find when you talk to a person that has designed privacy-enhancing technologies for a while, is that the ultimate goal is to reduce the trust assumption based on other entities that are not the user. So to minimize the risk of a privacy breach, what we try to do is to minimize the trust that we need to put on people to actually not have a breach. And we try to put technologies in place to minimize this trust. And we do this following different, what are these other entities? It's who we call the adversary, if you have ever read any paper about this. An adversary is also something that is differently understood in different communities. So if we're in the real world, what is called, what we call, actually Claudia and Seda called in a paper, social privacy is, okay, the adversary are other users. This is the policy, for instance, in Facebook. When I put something in Facebook, I configure my privacy policy that other people cannot breach my privacy. But I don't care about Facebook. Then if you move to the data protection type of thing, what they call institutional privacy, then the provider becomes semi-trusted in the sense that they have to abide to some principles about how much data they're going to collect, and they cannot process it for any purpose. They have to minimize, they have to be proportional, but this is still semi-trusted. But then if you move to the world of the academia and the privacy technologies, the adversary is everyone. We want to, again, to minimize the trust about any other entity in the system, the server, the network provider, or anybody that actually participates. And how do we get to this? We actually identified 6 different strategies that we try to follow in order to minimize trust. So we try to minimize collection. If you don't collect the data, you cannot lose it. I don't need to trust you to actually do anything with it. Minimize disclosure. So sometimes you need to collect some data, but try to minimize how much data is there. So imagine that I need to reveal, I need to prove that I'm older than 18. I don't need to give my date of birth. I may be able only to say, okay, I'm of age. So this is that kind of minimization of disclosure. Minimize linkability. If I have to give pieces of data at different moments in time or to different entities, I'm going to try to associate them to different identities so that they cannot be put together and they're used for profiling. Minimize centralization. Remember that we were minimizing trust. So one way of doing this is just give a little bit of information to each of the different entities in such a way that if they lose it, there is no loss, and all of them have to actually fail such that there is a problem in the system. This is what we call decentralization, decentralizing trust. Minimize replication. The more times my data is replicated in places, the more risk I have that this data is lost, and the more trust I have to put in more and more people that are replicating my data. And minimize retention. Even if you have to collect the data, have to disclose it, and you don't replicate, the longer in time you have it, the more risk of breach there is, and the more trust I have to put on you for this data not to disappear. Okay, that's great. So far, so good. These things look good. But now, again, the engineer comes to me and is like, okay, I believe you, but how do I use this thing? How do I get there? So we tried again to come back and make explicit the activities which we do mentally, like what is our mental process to come up to how do we use these strategies. And let me take as case study our electronic toll service. This idea came from actually an European electronic toll service that this is going to come into place. It was going to come into place, I think, last year. In the end, it didn't happen because of some economical crisis that, things got a bit delayed. But the idea here is that instead of paying taxes at a fixed amount of taxes per year, we're going to pay depending on how much we drive, which allow governments to implement what is called congestion pricing, which is something similar to what is done in the electricity or in the phone company, which is use different prices at different times of the day or at different roads so that you can modulate a little bit how people behave to alleviate congestion. And the example I used to place here was the Ring of Brussels. So the Ring of Brussels, if you live around here, you know that peak hours is a nightmare. So maybe by playing a little bit with the prices, we can make people not use it that much at that time. So we say that, okay, the privacy engineer, the starting assumption that they have, well, there is a well-defined functionality, which is this super important. Like privacy technologies, as any security technologies, do one thing. If you ask me to put a privacy technology that can do anything at the end of the day, then I have a very good answer. We have none. There is no privacy possible if you just want to be able to do anything. So here we had a well-defined functionality, which is we want to charge people depending on how much they drive and where they drive. Security, privacy, integrity requirements. We say users' location should be private. Do I need to argue why this is a concern? Or are we, in the light of time, I'm going to move forward. If you have questions, just please come to us. But of course, if we're not revealing locations, then we're humans. Humans cheat. We would like to pay less. So we want to put something in place that enables people to not cheat in the price that they have to pay. If I have driven that many kilometers in the ring, I should pay for each of these kilometers. And to start with this, we say the engineer has an initial reference system. And an initial reference system is a bit what any computer scientist from first year could come up when they are designing this system. So something very simple, we would say, okay, we want to know the location. We just collect GPS location on the car. This GPS location is sent to a service provider. The service provider looks where I was, makes some computation, bills, and then I pay to the toll authority whatever the bill says. Okay, excellent. Then the next activity that we do mentally is we classify these entities in different domains. The user domain, where the user puts their trust, and the service domain, which is where we don't want to put trust. In this case, the user believes herself, of course, I know where I am, my car, and my device that is in my car. This is what we call a local device, and we're willing to put confidence in it. We can discuss this elsewhere. Should we trust this device or not? But let us assume that for this case we do. And then the service domain, which is this part where we don't want to trust the entities that live there with our privacy. We trust them for other things. We trust them to do the correct billing, but we don't want to trust them to keep our information private. The second thing is identify what is the necessary data to provide the service. And this will also came very apparent that this is not something very easy to do. If you speak with a computer scientist student, they would just collect all the data and then think later which one they need. Actually, when you're a privacy engineer, you think from the beginning, which is the data that I'm going to need? And here, just to simplify, I would say we need location data to compute a bill. We need billing data to charge the user, otherwise how do they know how much they have to pay? We need personal data to send this bill, and we need payment data for performing the payment. And then how does this data go in this architecture? Well, the location data is collected in the car, then eventually we're going to send it to the service domain that is going to create billing data, send it to the user that is going to pay. And it may be that at some point the toll authority also has the location data for checking. And this is how services in the real world, if you think now about anything that you're using nowadays, basically any application that you have on your phone, this is the basis of it. Collect the data, send it to a service provider, the service provider does things and gives you back a bill or a service or something. So now comes the activity 4. How do we do to follow these solutions? So There are different technical approaches that actually implement these strategies. One could not send the data. One could encrypt the data. One could use what we call advanced privacy-preserving protocols. This is a particular form of crypto that enables to get magical properties, if you allow me the word. So we can do actually things in the encrypted domain that normally you would imagine we cannot do. Again, in the light of time, I'm just going to move forward. Feel free to ask questions. We can obfuscate the data. So instead of giving my location, like saying I'm in the ring, I could say I'm in Brussels. Or we can anonymize the data. I can send the exact point, but don't say it was Carmela who did that. So how do we actually play with these technical solutions to try to follow these strategies? The thing is that here, like I guess that you already have imagined the problem, is that we're asking the service provider, we need to trust them to keep the privacy of location data. So we want to minimize this. So we say, well, actually the location is not data. It's not needed for the provision of the service. We only need to know the amount that needs to be billed. Remember that the goal of this system was to make people pay for how much rows they use, not to know where they are and what they are doing, just to make them pay for what they have used. So the location data is not per se a requirement of the system. It's a means to get to it, but it's not needed. So we could just, using this technological solution, we cannot send the data. But now, of course, you will ask me, like in the beginning you said, I don't want people to cheat. If I don't send the location, how do I check that people actually have sent me all of the locations where they are? So for this, we resort to a concrete advanced privacy-preserving protocol called Cryptographic Commitments, which you can see as a vault. In a cryptographic commitment, what I do is take a piece of data, put it in on a vault, take the vault, keep the key myself, and send the vault to the service provider. So I'm committing that this is data that I'm going to use on my computations. And then at the end of the day, with my data, I will make all of my computations. Jesus Christ. Okay. I will make my computation. And what we're doing here is that we allow the toll authority to use cameras to make photos and ask me from time to time, okay, can you open one of these boxes that you have sent me with locations that prove that you have been here? So this means, like, as any other thing that we are used to do with governments in this kind of cheating mechanisms, is that we need to commit to every location that we have been in because we don't know where the photo is going to come. So by pushing these commitments to the service, we know that we're going to use, we're going to have to put all of the possible locations, and then this cryptographic mechanism also ensures that we have to use all of them in the computation and some other magic that I'm happy to discuss offline. So basically, we argue that this privacy in engineering makes, in a way, a very big change in the way that engineers reason. So the usual approach is, I want all the data. And then there comes the lawyer at your company and tells you, well, there's this thing called regulation. You maybe cannot have all of it. So you end with a little bit less. But actually, how we argue that privacy should be done is you need to think about what is the data that you need for the purpose. And then, because if you remove data, that you may have service integrity problems, these capabilities of cheating, then you may have to add a little bit more, which in our case were these commitments. And actually, in the end, you will end up with much less data than if you follow this other approach. And what enables to do this is what we call privacy-enhancing technologies, and also following these strategies that I have spoken about. So the takeaways, privacy by design is great, and we all want to get it. In this work, we made explicit privacy engineering activities in a way that can be understood by engineers. There are many things that we still haven't done. Like, we don't really have a fully fledged methodology, like requirements elicitation is still out of there. Pets are difficult to understand. They are difficult to manage, and I'm willing to take as much feedback as possible on how us, from the technology point of view, can help engineers using them, which are the APIs they are looking for, which are the notions that we need to teach them so that they can reason in the same way as we have reasoned in this design I have shown here. And the implementation is also hard. More and more we have more cryptographic libraries that enable to do this in the wild, but so far it's a bit of you need an expert on your company. And our current work is, okay, up to here we were working a bit on a waterfall world. where I have a design in the beginning, I have requirements, I go beginning to end. But if you are familiar with how software development and system development is doing nowadays, this doesn't work anymore. This thing called Agile has come into place, and systems keep reinventing themselves of the times. And it's not very clear how privacy technologies that are kind of very limited in their purpose, in the amount of things they can do, actually fit in the picture, and how this methodology that I have done, that is very top to bottom, fits in these super short cycles. And I would also be very happy to hear feedback on this respect. So thank you very much.
Thanks a lot, Carmela. I know that Carmela has another panel just after, so we have just time for one or two very quick questions. Are there any questions in the audience?
This means I did a very bad job, or I did a very good job?
Maybe I have a quick one to start if we have time. About risk, you started your talk by saying what we want to minimize is actually risk, and I agree with that. And so I was expecting some discussion about the link between risk analysis, or what we call now DPIA, which will be required with the GDPR, and the design phase. What do you think about that? For example, when you choose a particular technology or a particular architecture, usually or ideally this should be driven or motivated precisely by the need to reduce risks. So how do you see the articulation between the two?
So thanks for the question. So we see that as risk as very related to trust. With this idea that you minimize the trust in an entity, if you minimize the trust that you need to have on this entity, it means that you minimize the risk by definition, because this entity has not the power. If I don't need to trust the entity to have my data or to well behave with my data, I'm minimizing the risk. There is nothing I have there that is risked. In any case, the question is still how does this come into place? Not all privacy technologies allow, I mean, we do a bit of magic, but not that much magic that no data will be collected in the system. So at the end of the day, in my system, I removed the collection of location, but there was still billing data and personal data that are there. And there, for the data that I still have to collect after following all the process, that is not going to limit everything, all of these schemes come into place, and they are super important to understand what is the risk that is left after going through the design phase. Have I answered the question?
Thanks. Is there another quick question? Otherwise, I think we don't have time for another question. Thanks for your attention again.